Chapter 5.1 X-ray diffraction technique. The diffraction phenomenon. What is diffraction? Diffraction is a wave phenomenon in which the apparent bending and spreading of waves when they meet an obstruction. Diffraction occurs with electromagnetic waves such as light wave, radio wave, sound wave, and water wave. It caused by light bending. This is the diffraction phenomenon. The interference pattern of bright and dark lines from the diffraction experiment can only be explained by the additive nature of waves. Waves peak can add together to make a bright light, or a peak and through will cancel each other out and result in darkness. There are two types of interference, which is constructive interference and destructive interference. Constructive interference is the result of synchronized light waves that add together to increase the light intensity. Destructive interference results when two out-of-phase light waves cancel each other out, resulting in darkness. X-ray sources. X-ray properties in visible light is highly penetrating electromagnetic radiation of much shorter wavelength and has higher frequency than visible light. The wavelength range for X-ray is about 10 to the power of negative 8 meter to about 10 to the power of negative 11 meter. The corresponding the diffraction phenomenon. This is how atoms emit light. A collision with a moving particle excites the atom. This causes an electron to jump to a higher energy level. The electron falls back to its original energy level and releasing the extra energy in the form of a light photon. When an electron drops to a lower orbital, it needs to release some energy. It releases the extra energy in the form of a photon. The energy level of the photon depends on how far the electron drops between the orbitals. X-ray production. The production of X-ray is visible light photons, and X-ray photons are both produced by movement of electrons in atoms. The movement of electrons in atoms occupy different energy levels or orbitals around an atom's nucleus. X-ray can be produced in a highly evacuated glass bulb, and it's called X-ray tube that contains essential of two electrons, an anode made of platinum, tungsten, or another heavy metal of high melting point, and a cathode. X-ray diffraction and Bragg's law. Diffraction of waves by crystal is the diffraction depends on the crystal structure on the wavelength. The structure of a crystal can be determined by studying the diffraction pattern of a beam of radiation incident of the crystal. The beam diffraction only takes place in specific direction. By measuring the direction of the diffraction and the corresponding intensities, one obtains information concerning the crystal structure, responsible for diffraction. The Bragg's law identifies the angles of the incident radiation relative to the lattice planes for which diffraction peaks occurs. Bragg derived the condition of constructive interference of X-rays scattered from a set of parallel lattice planes. This is the Bragg's law.
Next, X-ray diffraction technique. Calculation of D spacing. We know that from the Bragg's law, we know the crystal can diffract an X-ray because the interference spacing in a crystal lattice is of the same order as that of wavelength of the X-ray. In powder X-ray diffraction, a finely polarized sample is probed with the monochromatic X-ray of a non-wavelength in order to evaluate the D spacing according to the Bragg's law. From the Bragg's law, we know that 2D sin theta equal to the lambda, where D is the lattice interference spacing of the crystal, theta is X-ray incidence angle, and the lambda is the wavelength of the characteristic of X-ray. From the calculation of this spacing, there will be constructive interference of the wave scattered from the two successive lattice points in the plane if the distance are equal. So, the increasing theta will be decreasing of this spacing. The minimum D spacing is lambda over 2. From this will be peak position depends on 2, which is the spacing of HKL and the systematic absence. From the X-ray to determine crystal structure, we know that reflection the angle of incident is equal to the angle of reflection. There will be constructive interference of the waves scattered from the two successive lattice points in the plane if the distance are equal. So from the picture, we can see the incoming X-ray have the same angle to the outgoing X-ray. So D is show the spacing between the planes. The outgoing X-ray will through the detector, so the diffraction must be in phase for the detectable signal. From the detector, we can look the X-ray intensity that show the peaks. The peaks will be referred to the theta C. So, from the Bragg's law equation, we can calculate D equal to n lambda over 2 sin theta C. Sin theta C allows the computation of the planar spacing. Cubic crystal structure determination is labeling the reflection planes. This is the first step using the Miller indices. A beam that corresponding to the value n above than 1 can be written as the n-order reflection of the HKL planes. For the example, third order reflection from 111 will be reflect 333 of the reflection. The second is the n-order diffraction HKL planes. For the Bragg's law, which is 2D over n sin theta equal to lambda, the n-order diffraction of the HKL planes of this spacing will look like the first order of spacing D over n. And the final answer will write NH, NK, and L is reducing spacing known as the reducing spacing, and this reflection we write similarly. For general equation of the Bragg's law, we know that n lambda equal to 2d sine theta, where the n is the integer and refer to the reflection of model. So for the example, it's K alpha radiation. For the example, is CU K alpha radiation show that lambda is 1.5 angstrom and the spacing 110 in meter is 2.22 angstrom. So this is the table that shows the order. Example n, sin theta, theta, and the description. The general equation of the Bragg's law in crystal structure determination is DHKL equal to A over square root of H squared plus K squared plus L squared. The Bragg's law that this Bragg's law equation can apply to the all set of crystal planes for the cubic structure. So the smaller of the spacing, the higher the angle of diffraction. The spacing of peaks in the diffraction pattern will be inversely proportional to the spacing of the planes in the lattice. The diffraction pattern will reflect the symmetry properties of. Thank you.
Hi, my name is Zulika Amira and I'm going to explain to you guys what is scanning electron microscope and how does scanning electron microscope works. And the third one, I'm going to explain to you guys about principle and the capacities of scanning electron microscope and the signal that produced by the scanning electron microscope, which are secondary electrons and the backscattered electrons. So stay tuned. For 5.2 subtopic, which is scanning electron microscope, we will cover how the scanning electron microscope works, principle and the capacity of scanning electron microscope, secondary electrons and the backscattered electrons. Do you know what is scanning electron microscope or SEM? Scanning electron microscope is a type of electron microscope that produces image of a sample by scanning the surface with a focused beam of electron. It is used very effectively in microanalysis and failure analysis of solid inorganic materials. It can perform at high magnifications, generate high-resolution image, and precisely measure very small features and objects. The electron interact with electron in the sample, producing various signals can be detected and that contain information about the sample surface photography and the compositions. The electron beam is generally scanned in a raster scan pattern and the beam's position is combined with the detected signal to produce an image. Specimen can be observed in high vacuum, low vacuum, and an environmental SEM specimens can be observed in the wet condition. How does scanning electron microscope works? The scanning electron microscope uses an electron instead of light to form an image. A beam of electron is produced at the top of the microscope by hitting of a metallic element. The electron beam follows a vertical path through the column of the microscope. It makes its way through the electromagnetic lenses, which focus and direct the beam down toward the sample. When it hits the sample, other electrons are ejected from the sample. Detectors collect the secondary or backscattered electrons and convert them to a signal that is sent to a viewing screen similar to the one in an ordinary television that can produce an image. This is the example of the image that produced by scanning electron microscope. This image showing an example of the green algae. Principle and the capacities of scanning electron microscope. The type of signal produced by scanning electron microscope include secondary electrons, backscattered electrons, characteristic X-rays, light, specimen current, and transmitted electron, but we will only cover the secondary electrons and the backscattered electrons. Secondary electrons. Secondary electron detectors are standard equipment in all SEM, but it is rare that a single machine will have detectors for all possible signals. The signals result from the interaction of the electron beam with the atom at or the near surface of the sample. In the most common or standard detection mode, secondary electron imaging, the SEM produces very high resolution image of a sample surface, revealing details less than 1 nanometer in size. Due to the very narrow electron beam, SEM micrographs have a large depth of field, yielding a characteristic three-dimensional appearance useful for understanding and surface structure of a sample. Next, for the backscattered electron. Backscattered electrons are beam electrons that are reflected from the sample by electric scattering. Backscattered electrons are often used in analytical SEM along with the spectra made from the characteristic X-rays because the intensity of the BSE signal is strongly related to the atomic number of the specimen. BSE image can provide information about the distribution of different elements in the sample. The advantage of the scanning electron microscope is it gives detailed 3D and the photographical imaging. Next, this instrument works very fast. And the last one is most scanning electron microscope samples require minimum preparation actions. Meanwhile, for the disadvantage of the scanning electron microscope is it's very expensive and large. Second, require special training to operate and scanning electron microscope, and the last one can carry small risk of radiation exposure associated with the electrons.
Hi guys, my name is Syafiqah Azwani. I'm going to explain to you the characteristic X-ray, sample preparation, and the schematic diagram of SEM. Stay tuned!
Characteristic X-rays. Characteristic X-rays are emitted when the electron beam removes an inertial electron from the sample, causing a higher energy electron to fill the shell and release energy. These characteristic X-rays are used to identify the composition and measure the abundance of elements in the sample. Sample preparation. All samples must be in appropriate size to fit in the specimen chamber and are generally mounted rigidly on a specimen holder called a specimen stop. For conventional imaging in the SEM, specimens must be electrically conductive, at least at the surface, and electrically grounded to prevent the accumulation of electrostatic charge at the surface. Metal objects require little special preparation for SEM, except for cleaning and mounting on a specimen stop. Non-conductive specimen tends to charge when scanned by the electron beam, and especially in secondary electron imaging mode. This causes scanning faults and other image artifacts. They are therefore usually coated with an ultra-thin coating of electrically conducting material, deposited on the sample either by low vacuum sputter coating or by high vacuum evaporation. Conductive materials in current use for specimen coating include gold or palladium alloy, platinum, osmium, iridium, tungsten, chromium, and graphite.
Do you know how is SEM functions? This is the schematic diagram of an SEM. In a typical SEM, an electron beam is thermionically emitted from an electron gun fitted with a tungsten filament cathode. Tungsten, normally used in thermionic electron guns, has the highest melting point and lowest vapor pressure of all metals. It can be heated for electron emission, and it is low cost. The electron beam, which typically has an energy ranging from 0.2 kV to 40 kV, is focused by 1 or 2 condenser lenses to a spot about 0.4 nm to 5 nm in diameter. The beam passes through pairs of scanning coils, or pairs of deflector plates in the electron column, typically in the final lens, which deflect in the beam X and Y axis, so that it scans in a raster fashion over a rectangular area of the sample surface. When the primary electron beam interacts with the sample, the electron lose energy by repeated random scattering and absorption within the specimen or interaction volume. So that's it. Thanks for watching.